Now, we'd like to begin Professor Ei-ichi Negishi's lecture. We would like to introduce Dr. Hayato Tsuji at the University of Tokyo, who will act as the moderator of this session. Dr. Tsuji, please.
Okay, good afternoon, everyone. Are you enjoying the meeting? Okay, thank you. So I'm Hayato Tsuji from the University of Tokyo. So it is my great honor to moderate this presentation by Professor Ei-ichi Negishi. He is a Nobel laureate in chemistry in 2010, and he is now the H.C. Brown Distinguished Professor of Chemistry at Purdue University in the United States. So he received his bachelor degree from the University of Tokyo, and he worked for Teijin chemical company for a couple of years. And while working, he received a Fulbright scholarship and obtained his PhD degree at the University of Pennsylvania. Afterwards, he joined Professor H.C. Brown's laboratory. He is also the Nobel laureate in 1979, and famous for his hydroboration chemistry, and at Purdue University. Then he was appointed to the assistant professor there, and via Syracuse University, he came back to the Purdue University to be a full professor in 1979. So his, of course, he received many awards, including the Nobel Prize, and his research interest is catalysis. As you know, the catalysis is a very important, and it plays a very important role not only in producing materials, but also in many fields like cleaning environment. So I believe that today his talk will be interesting and instructive, not only in the people in chemistry but also those people in the other field. So the title of his talk is Catalytic Asymmetric CC Bond Formation by a Zucker Reaction. So Professor Negishi, if you are ready, so please start.
Thank you very much. Okay, so what I need to do is this one? Oh, yeah. No. Let me try. Oh, no. Not this one. Here. Can you hear me? Yeah, good. This has little to do with the catalysis. Okay, as introduced by Professor Tsuji, I now firmly believe, after almost half a century of exploration, we need catalysis. We really need catalysis. And today, I would like to specifically emphasize the catalysis by D-block transition metals. D-block transition metals. And let's see. So, still, is this forward or? Oh yeah, okay. So, this is what I always say. You know, many people say that Negishi's chemistry is kind of expensive, using palladium, zirconium. And they say what is most important today is the CH activation. Well, it would be nice to be able to do that, with excellent results. But I think evaluation should be made in an overall sense. And I got this thing several years ago, maybe 3 years ago, when President Obama was saying, yes, 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 all over the place. So we should do organic synthesis in a yes, yes manner. But my thing, second yes doesn't have a why. I still don't know what why word I should be using. But a good synthesis, if you just think in a very common sense way, then we should actually obtain the desired product in high yields. That's why word. And we should get them efficiently in as short a step, the process as possible. Efficiency, E. And then we would like to produce preferably only what we want without producing any byproducts. I'm sure all of you agree with this. So that means selectivity is very important. So yields Y, efficiency E, and selectivity S. Why yes, that's yes. And then additionally, the whole process should be economical, E, and safety. This is where purity of some fine chemicals often becomes very important. S. So why yes, yes? So I tell CH activation people, there are several thousand of them today, if you can do your synthesis in a YES, ES way, containing economy and safety and selectivity, then I think that's fine. But if not, only because you make use of CH bonded species instead of using a CX bond or CM bond, that doesn't mean that your process is superior. I think it has to be evaluated in an overall sense. But in my opinion, to achieve this ultimate YES, ES goal, I think, you may want to consider something other than CH bond, like CM bond, that's organometallic, metal bond. And also you'd like to consider catalytic processes by using some expensive metals, that's what people say, like a palladium. And to explain this point, I often cite this the auto exhaust gas cleaning system. The dirtiest part of your car, there is this muffler, which you almost never see. And if you buy a new car, then you would be using this muffler system for several years without ever changing. But if you are young students, then you may buy a second hand and you may have to replace this muffler. But in there are several of the most expensive D-block transition metals. One is gold, another is platinum, the third one is a palladium, and maybe iridium. Okay. Imagine that I just learned from Dr. Tsuji that there are 1 billion cars on this planet. 1 billion. They all must have this exhaust gas cleaning system to get rid of CO and NO and so on, toxic gas. And the amount of this D-block transition metals that used is very small. In there, so comes CO or NO, and within a split of a second, I believe, it will be oxidized and it will be exhausted, exhausted. So this is a very, very persuasive example. And we all of us here, actually essentially all people on this planet must use this exhaust system. Otherwise, you may get a ticket or you may not be able to drive your car tomorrow. So I'm sure this clearly tells us it's not just the price of the material. And what is making this exhaust process so practical? That's a catalysis. And I haven't calculated the turnover number in this catalytic system, but it's got to be 10 to the 6th, 7th, 8th, 9th, maybe even beyond. But I have to be cautious because I don't know the hard facts. So this example should clearly tell you it's not just the cost of reagents and so on and so forth, but it is what is important is catalysis. If the catalysis becomes very efficient with a high turnover number, then expensive catalysts such as tetrakis, triphenylphosphine, palladium, which we use in our Negishi Suzuki cross-coupling, they becomes very inexpensive. If such catalyst costs $1 million per mole, if the catalyst turns over 1 million times, it is back a mole. Or maybe I should say $100, 100 yen, or maybe 1 yen per mole. Everybody has that. So cost becomes non-issue. That's why I would like to very strongly emphasize it is a catalysis that will help us sustain the good living on this planet into, in 21st century and beyond. So I want to present a little bit of my viewpoint in this lecture. Okay, so let's go on, but I'm still, okay. So after all, as Mendeleev, the founding father of the modern chemistry, already indicated, as shown here, some 150 or so years ago, this is our universe. Right now, Japanese Hayabusa and so on, those search rockets. They are shot, and they come back, and they bring some stones, tiny something present. And nobody has found anything other than those shown here. Right? So, and there are 112 of them shown in this one. But not all of them can be used in organic synthesis. So I tend to, this is my judgment, based on my own judgment. I tend to think that only about 70 should be considered. That's our arena, defining the scope. So those who are colored red, they are fundamentally radioactive. Some of them are artificial, as you know. And the polonium that is, oops. How to use a pointer. Okay. Polonium, number 84. After that, you see all red here, red here. Okay. So 83 is the number. And then, of course, here's a gray column, 5 of them shown, inert gas. Well, they're very useful in organic synthesis, but they do not participate readily into chemical reactions, right? So in organic synthesis, we can exclude them. Then there are some red-framed ones. I have shown about 7 of them, 1, 2, 3, 4, 5, 6, 7. they are toxic. In my opinion, intrinsically toxic. No matter how you use it, that is, mercury is toxic. People in Minamata, in Japan, they know. And thallium, and the lead, and the tin. Sorry, John Stilley's cross-coupling metal is a tin, but I check with pharmaceutical friends in pharmaceutical companies. They, including Aldrich Chemical, they cannot use tin. They must write signed agreement not to use tin. Okay, and this AS, milk containing this thing kills many, many babies. Okay, so we exclude these intrinsically toxic metals or elements. Then we are left with these green, about 10 dozen of them. Those are organic molecule constructing elements which we must use. 10 or dozen, green. What else we have? We have about 20 or so, this blue guys. They are main group, so-called main group metals. Many of them are not so toxic. In fact, people may have been still suspecting toxicity associated with the boronic acid, boron. But to my knowledge, nobody has found any toxicity, so to speak, associated with zinc. Zinc is very essential. It's needed for our, life. But this one appears to be so safe. Safe to the baby. There's a milk box shows this zinc. Anyway, so we may use these blue main group metals, even though, most of the time we tend to use them in a stoichiometric way. And what else do we have? Then we have this, 3 by 8, 24, this golden block. Color gold is chosen by me. Anyway, except for this artificial and radioactive technetium, which cannot be readily incorporated in our organic synthesis, we are still left with 23, is D block. This is the D block. D block transition metals. And as I said, all of those, gold, platinum, palladium, iridium, they are clustered here. These are dispersed in your muffler system. And they are very, very expensive, but effective cost is dirt cheap. Besides, have you ever replaced, after buying a new car, have you ever replaced a muffler before you trade it in? So you should appreciate the level of catalytic turnover number. Maybe 1 billion times. I don't know. Don't quote me. Okay, so these are the ones which are so promising in trying to, save our civilization during the 21st century and beyond. So that is, without persuading you, I am just saying this. Okay, so let's see. What else do we have? Well, actually, so it's really reassuring that universe is defined by Mendeleev, pretty much. And we don't need to, we cannot spin out of this Mendeleev-defined periodic table. There's nothing else outside. Well, of course, he only had about 80% of them, about close to 90. But it's amazing, isn't it amazing? You know, some century and a half ago, he had this already, you know, displayed in this way. And if you go to St. Petersburg, I really recommend you to take a bus or something, taxi, along the Moskovsky Avenue. And this is a wall, side wall of the Mendeleev Institute, Moskovsky Avenue in St. Petersburg. I recommend that. Oh, here it is. Here's Mendeleev, one of my heroes in science, along with Newton and Crick Watson and others. Anyway, so well, I'm going to have to skip. And it goes back to the time when I was at University of Pennsylvania, when I was 26 maybe. Am I right? 31. Sorry. Yeah, 26. I haven't even graduated from University of Tokyo. But anyway, in 1962, my second year as a PhD student, I came up with this Lego game, concept of Lego game, like a synthesis of organic compound. So if you have a piece A with a hole, and if you bring a piece B with a stick, then you snap it, then you get A and B. This was the origin of my cross-coupling work. And A can be replaced with A prime or whatever, B or C, D, or G. B can be also substituted with many things. All you need is a piece with a hole, maybe an acid, and a piece with stick, maybe a base with the 2 electrons, snap it. Then you should be able to synthesize. So I was so excited about my idea at the age 26. 26? No, 31. That was, sorry, 62. Anyway, then I checked the literature. And I noticed that with magnesium as M, that's a Grignard reagent. It was known, they are known to react with organic electrophiles like halide, and then give you this Lego game-like way, various organic compounds. But then I seriously surveyed the literature, and what I found was what is shown here. So these are typical organic organometallic species, about 10 of them, covering wide range. And here, likewise, you can list about 10 of them, close to 10 of them. Anyway, so all these, as you may know, when your halides or organic electrophiles are of this type, in other words, containing unsaturated carbon group, virtually nothing works by Grignard reaction. Sometimes with the lithium compounds, they swap, M and X swap. Then you may luck out. But by and large, you cannot do this. And outside this miserable area, even outside this one, sometimes Grignard reaction synthesis works, but often, you're surrounded with the trouble. So that was the picture. Okay, so what happened? After we discovered the palladium catalyzed cross-coupling, it's got to be palladium. I don't discuss this in detail today, but Professor Tamao was a pioneer in this business. I started doing this in 68, but I got this one in 76. In meantime, Professor Tamao showed that with nickel, you can do some of these things. But it's much more limited. And with the palladium, you can achieve, well, you can cover maybe 2/3 of the whole territory in a very satisfactory way. So this is the one which was appreciated by the Nobel Foundation. I tend to think so. But still there are some no territory. Luckily, in this area, no matter how you try, there are all kinds of troubles. But you can avoid those troubles by shifting from this to here, 3x3 matrix box, to this one. So you don't need to do this, you do this. But anyway, that's not an important story. So how did we come up with this, this scheme and then the palladium? Okay, that's the story. Well, first of all, from Professor Brown, my Professor Brown, boron hydride will readily add to this double bond, but let me just show you the power of metals. Metals, they tend to be Lewis acidic. In other words, electron deficient, right? So if you mix alkanes with alkenes, really nothing happens under ordinary conditions. But if you just replace this thing with carbocations, then they will readily react. The power of Lewis acid here, and the metals, metals. So these two are nominally said to be isoelectronic. Okay, and if you go from here to here, you observe a tremendous acceleration. And if you're noting the isoelectronic structural relationship, now you try this Brown's hydroboration, and it goes room temperature like a shot, 0 degrees like a shot. Minus 25, yes, okay, it goes. Even at minus 78 degrees, reaction is slower, but it proceeds. And we can understand in this term why these reactions go so fast. And later, this hydrozirconation was not our discovery, but when we replaced boron with zirconium, you just focus your attention and place metal here, HM, this empty orbital, HM, and empty orbital. They work in the same way. So these are the things that Fukui in Japan was seriously studying during the World War II with a paper and pencil, maybe, with a grinding calculator or something. So we owe him a lot. But then why doesn't Grignard reagent work so well? Well, I kept wondering about this for many years, and I came to the same kind of conclusion, but in a sort of my own way. But in a form of publication, actually, it is a fairly recent paper, 10 years ago, by a group of theoreticians, let me see, across from Taiwan. There's a Chinese university, Chinese group, They published in JSCS. And then they told us, they showed, that this undesirable energy increasing interaction, that is hindering the reaction of Lewis acid with an empty orbital and a Lewis base with two electrons. You might think that if you mix acid and a base, then they go bang, then you get a salt. But what they have shown is that if this is all they have, and then interaction between the two will give the salt thermodynamically more stable, but with a high kinetic barrier. What is this? What is raising the kinetic barrier so high? Well, you imagine that these two begin approaching. Let's assume that both are neutral. It doesn't matter. As they approach, the base begins to donate electrons. And then you reach this point. At this point, A, as it has already begun accepting electrons, so it will be negatively polarized. And B has begun sending electrons, therefore it will be partially positively polarized. The effect of this polarization is that this negative charge in electrons are of course negative. They start repelling. Don't come. As Lewis acid initially said, come. And now at this point, go back. The B, neutral here, begins to transfer electrons. Then it will be positively polarized. And this polarization begins to tell these moving electrons, transferring electrons, come back. So that will raise the kinetic barrier very high, even though thermodynamically it may be downhill. So how to solve this problem? Well, here's the problem, solution. I believe it came originally from Fukui. So based on Fukui's homo-LUMO interaction theory. And I understand he was doing this during the World War II. But his first paper was published, I understand, is 1971. Now, already in 1973, this particular scheme was reported by MJS Dewar in UK. Okay, so it's generally called Dewar's synergistic bonding scheme. Okay. So we just learned from this previous slide that one-way two-electron transfer between acid and base, kinetic barrier can be undesirably high. But if you consider homos and LUMOs and homos and LUMOs of your reagent, for instance, olefin, Fukui says, olefin you have a pi bond, 2 electron, homo. But don't forget, equally important, similarly important is another molecular orbital, just one above, where there may not be any electron. That's a LUMO, this butterfly-shaped LUMO. So he taught us to consider simultaneously HOMO with 2 electrons and the one above, LUMO. And he won his Nobel Prize in 1981. Okay? And we do the same thing, with everything. So here is D-block transition metal. And as you know, by definition, D-block transition metal, they can have similarly one filled and one empty molecular orbitals of similar energies. So here's a HOMO, and here is a LUMO. No? Okay, so if you consider, and then if you consider their HOMO-LUMO interaction schemes, then two electrons, pi electrons, can interact with empty orbital LUMO of the transition metal. You have to have transition metal. You can have this one maybe with others, but advantage of transition metal is that many transition metal species can exist in this form as a thermally stable species. You can put on the shelf, keep the shelf. We keep several years or more. Really, they stay stable. And Aldrich Chemicals and other chemical companies sell them in this form. They sell transition metal complexes in this form. They're thermally stable, and yet chemically they show a magical power because of this availability of low-lying LUMO and HOMO. Okay, so two electrons in the middle, they go up from olefin pi orbital to transition metal empty orbital. In turn, simultaneously, this butterfly-shaped HOMO of, let's say, palladium, can be back donated to the LUMO of olefin. This is the thing that people didn't used to consider. Olefin has a pi orbital, but people didn't used to think that pi star orbital is very, very important. LUMO, as a LUMO. So polarization, has an ill effect. I just showed you, but polarization here plus minus polarization is pretty much canceled by polarization in the opposite direction. So this will have a significant effect in lowering the kinetic barrier. Lowering the kinetic barrier, that leads to catalysis. And these species, unlike carbene, Professor Noyori's favorite, carbene has a HOMO with two electrons and LUMO, empty orbital, but I have never seen carbene. And it's very unstable. Once it reacts, then that's the end of the story. But so this is important, but the other important thing is that they can be separated, reversed, readily. So it's like a cyclopropane and the reverse, because both ways energy barriers are relatively low. So that's the key, one key to the, at least one, the very significant key to the successful use of D-block transition metals as a catalyst. As shown here, palladium sneaks in, and then with very efficiently, it can do the same with this carbon iodine sigma orbital, and then it will slide into this place, and then that can be replaced with palladium, using our cross-coupling. So, and no wonder this one is much more reactive than this one. Anyway, so that's one of the very, very important secret. Okay. And but of course, the other one which you should not forget about is that this process can be readily reversible. Barrier is low. And many processes involving D-block transition metals are readily reversible. Otherwise, you have a difficulty in making good use of them as a catalyst. So they can go up the oxidation state and do something, and then eventually they can be down, reduce down to the original oxidation level. Very easy in a very arduous fashion. So this explains why they can be reused and recycled many, 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 many times. Okay, and this is probably the most important part of my talk today. But I want to add another very important part of my talk today, right here. If you accept this power of the synergistic bonding, a la Fukui, then look at this Brown's hydroboration or whatever. Hydroboration is very fast, and very selective. 100% syn addition. How can you explain? No problem. So you just replace this D block transition metals with this boron, let's say, metal hydride. Doesn't have to be boron, but metal hydride. And as you know, borane is a six electron species with one empty orbital, available. So this acts as a HOMO, this acts as a LUMO, just like this. Two electrons go up, 2 electrons go down. This is a very, very important thing to lower the kinetic barrier. No wonder hydroboration or many other hydrometallation reactions are so fast. That's one point number one, and so selective. As you can see, if these are sticky, reaction, in other words, they don't go once they come close and start working on each other, then they just do this, and you can readily appreciate 100%, essentially 100% syn addition of metal hydride. And for that matter, learning this, many others have replaced Brown's boron with zirconium or many metals. Okay. Now, if you accept this mechanism of hydrometallation, just replace this hydrogen with whatever, carbon. That's what I did. And in fact, we discovered carbozirconation of actually acetylene, not olefin, but olefin can also be shown, this can also be shown. So you can have a carbometallation. And we found our first one in 1978. And I coined this carbometallation. If you discover new type of reactions, you have the opportunity to name some such, these reactions. Hydrometallation. I said we should call these reactions carbometallation. 1978. If you find the literature in which this term was already used before me, let me know. But so I'm pretty sure that we were the first ones. But why so are we so proud of it? No, I'm not. We are not proud of it. I want to tell you that we were attacked by my senior colleagues. What are you doing? Are you messing up our teaching, chemical terminology? So I said, why not? I mean, these are new reactions, and if this is a hydrometallation, which proceeds in 100% syn fashion, the related carbon metal addition can be called carbometallation. And as you can imagine from this analogy, many carbometallation reactions are essentially 100% syn. There are some others, but there must be some side reaction, but as can be seen here. But we have just covered hydrogen and the carbon. So remember Mendeleev's periodic table. You can replace this hydrogen or carbon there's no reason why we cannot replace this one with electropositive metal. There are a whole slew of metals. And we have indeed, we're still exploring what I would call a metallometallation. This would be my name. And we have discovered heteroatom metallation. And I call this heterometallation. Doesn't sound so comfortable, but I bear with it. But heterometallation, when the metal is a boron, was already discovered back in 1964, shortly after Brown's hydroboration. The haloboration reaction was discovered back in 1964 by a British chemist. I forgot his name. I should remember. So it works. And then you're right, as you would predict. This is a strict syn addition, 100% syn. So as you can see, with the metal here, you have many choices. You can change this this part from hydrogen to carbon to a whole slew of metals. There are about 50 or so metals that we can think of, and this even electronegative one. So if you come to this electronegative one, halometallation, I told you haloboration reaction is a very useful reaction. And you're right, as you would predict, 100% syn addition reaction. But the scope of this halometallation, I would imagine, is rather limited, because metal halogen bond, most electropositive, most electronegative, the thermodynamic is strong, then you break it, that could be contra-thermodynamic process, then it's a no-no. You have to do a major modification. But luckily, boron is sufficiently electronegative, so haloboration reaction is a synthetically very useful reaction. Okay, I think I have, with these two slides, actually, I can stop any time, because these are the ones that I wanted to tell you. And with these simple, well, first we start with this Mendeleev's periodic table. Okay, knowing our arena, the number of elements, about 70 of them we can use, of which maybe 10 or so are organic. The others are metals and others. So, and then you can keep discovering, I hope. So, I don't dwell on detail, because that's not but our mode is, for instance, with this reaction as a model, cross-coupling, acetylene and aromatic, okay? And I can go ahead and tell you, this palladium catalyzed cross-coupling is really faithful. You can retain the stereochemistry and all kinds of finer details. Retain 100% of it. And I don't have time today, but we have developed many asymmetric, catalytic asymmetric CC bond formation. The final CC bond coupling is done by our cross-coupling. Once we make a chiral group pure, then our palladium catalyzed cross-coupling does not mess up. We can also use copper and magnesium, nickel, I'm sorry, without messing up any part of the two pieces. We can couple. So if you make a simple intermediate as optically pure, enantiomerically pure species, then you can make a enantiomerically pure organic compounds, all kinds, in high yield. So we claim that the cross-coupling that retain essentially 100% of the structural details. They just Lego game-like fashion, they just couple. Okay, so in fact we we would like to claim that we have demonstrated them all before some others. Some other names are shown here, and we show that in addition to Grignard reagent, the zinc works very well, and the boron works very well, which we eventually published in 1979. And my friend, Professor Suzuki, took over, but he took over since 1979. And John Stilley's tin works maybe the third best. So today, these two, in a hard job, I think ours outshines others. But for relatively bulk production and so safety-conscious people and so on, this might be an option. But we found them all. And turnover number, as you can see, million plus. So $1 million of more reagent is a buck more. $1 more with a million turnover number. That's what I said. And as I said, if you prepare your intermediates precisely, then as I was telling you, cross-coupling doesn't mess up any finer details. So this will, any structural features like this under our kinds of conditions can be retained. And this applies to asymmetric center. Of course, you have to be a little careful in what you do, but you can retain essentially 100%. So we recently published this one in Chemistry European Journal, but this is a part of a very extensive molecule. And this is Professor Yoshi Kishi's molecule, but he likes our reaction. He liked our reaction. He started using this one extensively. And so today I'm going to have to skip all these. And to show you the selectivity of this reaction, I want to just give this one and stop my lecture. So here's octenoate, the 1, 2, 3, 4. Anyway, triene. And with the 3 double bond, 2 times 2 times 2, 8 different isomers are available. And no one had previously prepared them all as a pure, ultra pure species. Let me see. At this point, I think we are settled with equal to or greater than 98%. We don't see the other, the isomer. But anyway, as you can see, all trans. So I just want you to scan the yield of the final critical coupling process, hooking together. So intermediates are made pure, then they will cross-couple pure. And the purity is shown here. All we don't see, essentially don't see in a, normal analysis. We didn't jack up the level of analysis in this work because we are so happy. So 1, 2 with Z, 3, 1 Z here, and 4. These are more easy of the 4. Now, 5th one, Z here in the middle. Put the Z in the middle was somewhat more laborious, but as you can see, essentially it works very well, high yield and in high purity. 7 and 8. So Z, Z. So this one is Z, Z, Z. No one else had made more than 4 of these. They tried to make 8. But the 4 was roughly the record number, but we beat them all. But with no effort, as you can see, because the method is so good. Okay, so now things like a CoQ10, my wife is forcing me to take pills. So likewise, once you make this one, this piece, and this piece, and then cross-coupling will take care of them. Okay. First, second, and I think I see 9th step. Anyway, but all these red colored bonds were synthesized, and of course, this is yet another story. This is one of the sort of last bastions in organic synthesis. How to make chiral, no double bonds here, chiral compounds with absolute stereochemistry in high EE. And now we have finally reached a level. You give me the structure, we will make it. And how pure? Well, as pure as you specify. If you want a 99.9999% EE, we'll make it without much effort. Routinely, we can make it. But that's another story. So with this zirconium catalyzed reaction, and of course, you have to do it right. You have to do everything right. But so I'll just give you one most recent example. So clearly, the ultimate level is something like this. So here at this point, asymmetric carbon center, if you go this way, you hit methyl, CH3. If you go down this way, you hit CH2D. So only difference is that one of the 3 hydrogens is replaced with a deuterium. So we call this isotopomer, right? Isotopomer. But it is still very, very, very pure. And as I said, if you want a 99.9999% EE level, we will make this guy 99.999% through lipase catalyzed acetylation. Then thereafter, our coupling chemistry is so pure, we have never seen any isomerization or mixture formation. Believe me. So this one is even more difficult, as you can imagine, no problem. Different here only by the presence of isotopes. And we don't cheat, of course. So here, for instance, racemic one shows 2 big one in the middle, and 4 signal pattern here and here. But if you make it pure, then you see nothing for this position. So you know that it is really pure, okay? And yeah, we did this within the last year, so I'm very, very proud of this. And we have finally reached the last stop. And okay, so this is a very remotely chiral. So if you move away from this OH center, oxygen-bearing center, then if you make it longer and longer, then you would imagine that it would be more and more and more difficult because the chirality is going to be more and more feeble, very, very weak. In fact, in many of these compounds, we don't see any optical rotation. So we rely on NMR, and this is a moisture ester analysis was very useful, but it has a limit. And some Japanese group in Tokyo, they modified the moisture ester from phenyl to naphthyl here, CF3 to methyl. Those are the only two changes. But theirs is much superior. So we can tell the difference in such a remote place, alpha, beta, gamma, delta, epsilon place, where one side is ethyl, the other side is propyl, or even isotopomeric. We can tell the difference, and we can synthesize them very pure. This is a 1-to-1 mixture, 12 signal pattern. This one is pure, only 6 signals shown. Sorry, I just show the ones who actually did the work. These are cross-coupling heroes. And this is Van Horn, the hydro and the carbo zirconation hero. Arguably, my best postdoc comes from St. Petersburg, where Mendeleev used to work, Denis Kondakov. And some recent work. More recently, my group is dominated by people from one country, giant, big country. Oops. It's hard to, this was a reunion a few years ago, and thank you very much. Sorry for going way over time.
Thank you, Professor Negishi, for your talk about the cross-coupling reaction and the detail about it. I think we still have time to accept 10 minutes.
Okay, I'm glad to hear
Okay,
that.
so if you have a question, so please raise your hand, please.
I'm very impressed by the 99.99% synthesis.
So am I. I wasn't expecting, I didn't think that it would be possible, but now we got better and better and better. We learned a better trick and so on. And now it seems that it's endless. But now the limit is analysis. I ended up buying a very expensive GC and LC and so on. And then I said, no, I cannot spend more money on these. And then actually we went out of that GC-LC range. And what remained was an NMR. And early on, when distance is still short, distance between OH or some functional group and the chiral center is short, we were able to make use of a moisture ester analysis. But when we separate them, then right now the only one that works is that Tokyo Institute of Technology guy invented modification of the moisture ester analysis. But sorry to interrupt your question.
I see. So it seems to me that the catalyst had to be finely tuned to make a specific product. Mm-hmm. So my question is, how difficult is that?
Well, to develop cross-coupling, I thought about this sort of thing, Lego game thing in 1962. I first found, I thought I first hit the jackpot in 1976. So that is a 14-year effort, And then that's 76, and then by 77, we covered the whole territory, and several options were found. Zinc and palladium, in most cases, is the best. Not only safe, but it's chemically best. But people don't use, and people use this as a last resort. Many young people, typically European people, they come to me and they thank me, shaking my hand. So what are you thanking for? I tried this method, that method, this, and finally this Negishi coupling with the zinc and the palladium. That worked, and I was able to complete my PhD thesis or something like that, So quite often I get congratulated in this way. But that was my point. The point, my answer to you question is the one that I was emphasizing early on. It's a very reassuring that we only have about 10 or dozen organic elements and 50 or so metals, and 23 D-block transition metals. And we know that early D-block transition metals have this kind of tendency. The late one have this kind of general tendency. And then there's in the middle, some in the middle. And then lighter ones and heavier ones. There's a trend. All taught, explored. I guess Mendeleev didn't explore everything, but actually we know the limit. That's the universe. We cannot spin out of this. That's really reassuring. And of course, hard work. As I said, it takes time. So that's how we have found all these things. Did I answer your question? No.
How to purify that catalyst?
Purify catalyst? Well, so which one? Asymmetric one?
Some chiral symmetry.
Yeah. So we make a highly chiral, highly chiral one. How should I say? Not the feeble one, strongly chiral one. That means chiral center is close to OH. I'm sure we start with aryl alcohol, things like that. And then in alpha position, there is a substituent. And so the compact molecule. Okay. And then you can use this Japanese company, Amano Chemical. They sell whole slew of enzyme catalyzed separation, acetylation. So that's easy, and most of them can be done when the structure is compact and asymmetric center is right next to CH2OH and so on. You purify as much as you want. So this is where you go up to 99.9999. Well, we typically stop at 99.9999% EE level. We call this pure. And we know that if we wanted to go beyond, we can go. But it's not, it's not very interesting to us. So once we make that, but that one has iodine, iodomethyl also. Iodomethyl, hydroxymethyl, and the alkyl group here. Then you use this one, and then you move this chiral center around using a cross coupling. So from alpha position to beta, gamma, delta, we have gone to epsilon position, and so their rotation, optical rotation becomes near zero. Many of them don't even show, don't move. But we have this NMR tool, and we have gone to epsilon next one over with this naphthyl thing. NMR. With NMR, we can still tell how pure it is. But rotation is essentially zero. But they're still chiral. Very, very feebly chiral. So we claim that we have covered the whole range. And probably the most delicately chiral compounds. And we believe that we can make essentially any of those with our Zaka reaction. I call this a Zaka reaction. Zaka reaction, I got a cue from Ziegler-Natta polymerization. In Ziegler-Natta polymerization, they want to produce a long polymer, with many asymmetric center. But they were only interested in diastereochemistry, tacticity. So all R and all S, for them, doesn't matter. But we need to specify more clearly. But ours is a one-step, so what we do is a one-step Ziegler-Natta reaction. And to discover this reaction, which we call a Zaka reaction, it took us 17 long years plus genius from St. Petersburg, Dennis Kondakov. So if you think that what you are doing is right, convinced, then keep trying good things, then I feel that they will come, especially in good guy's hand. That's my feeling. Okay?
So maybe we can accept one more question.
Yeah. Uh-huh. Okay.
Sorry.
Yeah. We'll take two. Huh?
Shall we take?
I should answer in a more
Okay, please.
brief manner.
So the last question, please. Microphone.
Someone. You can beat me.
So at first, thank you very much for the concise and informative lecture about the world of catalysis. So I am wondering, when you explained about the interaction between homoloma of metal center and the organic molecules, so it was surprising you considered about replacing hydrogen by carbon materials. But in chemistry, the hydrogen is usually can form the positive ion, but carbon always prefers sharing.
But relative to metal.
Oh.
Yeah, metal will always be positive, more positive. Relative to hydrogen or carbon or metal. Okay.
My question is finished.
Okay. Yeah. Yeah, you have the microphone. So sorry, microphone is not working.
Okay, nice working. I want to ask you a question about what you think about the future of reaction development, because when you look at transition metal catalysts, they have revolutionized the way people make materials. And after the cross-coupling reactions, which were very important, recently we have the CH bond functionalization. And there's a lot of debate about this CH bond functionalization, whether it's useful.
I have a lot of criticism about it.
Yes, a lot of criticism. So from that base, what do you think about the future of reaction development using transition metals? And looking at the problems that the society is facing, especially the pharmaceutical companies, what do you think the people who develop reactions should put more emphasis on in order to solve those problems?
Thank you. This is what I have been saying loudly. We have to deal, a cross-copying. It's may have reached a plateau, high level, but we need to deal with some waste kind of organics, especially CO2. It's easy to make use of CO2 just by treat CO2 with a Grignard reagent. You get carboxylic acid, and that would be a good source of fat or maybe energy. But that won't be a winner. That's not economical. So we have to go catalytically, and I know that catalysts almost have to come from D block, but a combination with something else too. So this is catalytic CO2 reduction. There are, I say, multiple number of Nobel Prize waiting for you, for sure. But you have to do it right. No one, to my knowledge, no one has it done. I may be wrong. If it's a very recent development, then I have been too busy to learn. But there's nothing more interesting in my mind as a chemist, as organic chemist, than this thing. But in the meantime, I have proposed that to JST, Japan Science and Technology Agency. But we have had this asymmetric thing going up and up and up. And only at the end of last year, I felt we have conquered the top of that activity. So it takes time, but it's wide open. Anyone can do it. With a big award, just shaking.
Okay, thank you very much. Because our time is limited, so I would like to close this session. So please thank Professor Negishi again.
Thank you very much. Thank you very much, Professor Negishi and Dr. Tsuji. Well, tonight we have a reception from 6:30 p.m. I know we haven't got much time. In the Prince Room, located on the basement floor on the Grand Prince Hotel Takanawa. The room is located in a different building, so please make sure that you follow the staff guidance and signs to the reception room. Please make sure you take all your belongings with you, and nothing should be left in this room tonight. I would ask you to move to the reception room without delay. So tomorrow, the morning sessions will begin at 9:30 a.m. in this room, the same room. We hope you enjoyed today's program, and see you at the reception. Thank you.